Hey there, welcome back to Calc 2. In this video lecture, we're starting the second section of Chapter 11. So we're going to spend 2 lectures in it. In this first part, I just want to introduce the notion of an infinite series. I want to look at as many examples of infinite series as I can, and then establish one of our, what will be many, what we'll call convergence tests for infinite series. It's called the divergence test. Okay, so that's just kind of an outline, maybe more for me than you. Let's get going here. So, what is an infinite series? Well, it starts off with a sequence. Somebody gives us a sequence. I'm going to kind of color code these things a little bit later on too. So I'm given a sequence A sub n. Yeah, we've been talking about sequences in section 11.1, so you know what that means. And then I'm going to form a new sequence. It's going to be denoted by S sub n. The S is short for sum. It's called the sequence of partial sums. And then I'm showing you how we define it down here. The first element in the sequence S is just the first element of A, the sequence A. But then the second S is the sum of the first 2 A's. The third S is the sum of the first 3 A's, and so on. So this nth partial sum, the nth partial sum, I'm generating a new sequence. I find it, it's a number, and I find that number by adding the first n terms together in the sequence an. In fact, yeah, so I add a1 plus a2 all the way up to an. I call the result Sn. You can write that down in summation notation. I'll just write that it's the sum as k goes from 1 to n of the terms a sub k. Yeah, I can't use the index n down here on the a's because I'm summing from 1 to n. So that's why I had to change the index to some other letter that chose k. All right, so that's the nth partial sum. So that's the sequence of partial sums that comes from a given sequence an. All right. If that limit, sorry, not if, but the limit of that sequence of partial sums, we write it using the same summation notation, but I write k goes from 1 all the way to infinity. So that infinity symbol just means that we've taken a limit. So you can think about it, it's a1 plus a2 plus a3 plus never stop. It's a so-called infinite sum. But what do I mean by an infinite sum? Because we can't actually add infinitely many numbers together. I mean a limit. I mean, form these partial sums with more and more terms, and then ask yourself, what happens to those partial sums as we add more and more terms? So that thing, that limit, is called an infinite series. So a series is a limit of a sequence of partial sums. And the AKs are called the terms of the series. They're the things that we're adding together. And I'm using this color coding because when students usually first study this stuff, there's a tendency to confuse these two objects, to confuse the terms that we're adding together, the AKs, and what they add up to, the SNs. So throughout this lecture, I'm always going to be coloring the terms red and the partial sums blue. And that's just to try to sort of help you distinguish that they're not the same thing. The things you're adding together are not the same thing as what they add up to. Okay, we're going to use similar language that we do for sequences. If that limit exists, then we'll say the series converges. So we're going to say the series converges if that limit of partial sums exists. If the limit of partial sums doesn't exist, then we say the series diverges. Okay, let's look at a specific example. So I've got a series here. It's the sum of, as k goes from 1 to infinity, of 1 over k. So what do I want to do? Let's just write out some of the terms of that thing. Let's write it out in longhand. So you always start with the counter down here. K equals 1 is the first term. So the first term in this infinite sum is 1 over 1, or 1. And then when k is equal to 2, the term would be 1 over 2. And then 1 over 3, 1 over 4. It's an infinite sum. Sometimes if you want to stress it, you could write the kth term out here, but you always have to end it with those ... dots. There is no end to it. And again, we're not ever going to add up infinitely many numbers. You cannot do that. You cannot perform an infinite number of operations inside of a finite lifetime. However, we can add more and more terms to this thing and ask, like, well, what are they doing? What are they approaching? Let's just look at some of the partial sums just to convince you that we really are just doing arithmetic, and also to remind you of what partial sums are. So my directions are to find S1, S2, and S3. Well, S1, you remember, is just the first term, so it's just 1. S2 is going to require a little bit of arithmetic because we have to add 1 plus a half. 1 plus a half is 3 halves. So the second partial sum of this series is 3 halves. S3 would be 1 plus a half plus a third. All right, so if you want to actually do the fraction arithmetic here, we have to add 3 halves plus a third, the new term. We'd have to convert all of that stuff to sixths. So I think that 3 halves is 9 sixths and 1/3 is 2 sixths. And so you add those together and you get 11 sixths. So our first 3 partial sums are 1, 3 halves, and 11 sixths. Okay, I don't know if this series converges or diverges. I haven't looked at enough terms to try to see a pattern for that. 3 halves is bigger than 1, and 11 sixths is bigger than 3 halves, but I don't know if those numbers just continue to keep getting bigger, or those are the partial sums. Yeah, the terms we were adding together, those things are the terms of the sequence. So in my color coding here, well, I'm not going to color them red, but the AKs are the things that we're adding. The things I colored blue are what they add up to. I do want to make a remark about notation here. I'm sorry that this slide got a little busy. But if you look at my note down here, first of all, the name of the index is completely irrelevant. I can write the sum as k goes from 1 to infinity of 1 over k. The sum as n goes from 1 to infinity of 1 over n. You know, you can write the sum as Tyler goes to infinity of 1 over Tyler, as long as Tyler is understood to be the name of the variable. It doesn't matter what you call it. And for that matter, there's no special place that you have to start. This sum would be the same as adding from, say, 0 to infinity of 1 over n plus 1. Because notice in that last formulation, when n is 0, well, the first term in the series is 1 over 0 plus 1. That's a 1. That's the same as before. When n gets to 1, you'd have 1 over 1 plus 1. That's 2. So just like with sequences, there isn't one and only one way to index them. You can index a series any way you like. You can call the variable anything you like. The one thing you can't do is in an expression like this. Sorry, I'm going to have to erase some of that. What I can't do is call this value and this variable and this one can't have the same name, because you cannot let one variable range between something and itself, right? So it makes sense to say let k go from 1 to n. You can't let n go from 1 to n. Well, what would that mean? Yeah, good. Okay, let's look at a second example. Let's look at a second example. This example, my AKs are 1/2 to the k. And I wrote them out ahead of time so we can go a little bit faster. So when k is, and we're starting this sum, by the way, at 0. We're starting this sum at 0. So when k is 0, you get 1/2 to the 0. That's a 1. Yeah, so that's my term. When k is 1, I get 1/2 to the 1, 1/2 squared, 1/2 cubed, and so on. So the terms are those powers of 1/2. All right, let's write out some partial sums. The first partial sum, it's just the first term. So I'm going to still call it s sub 0. It's the sum of the first, even though that corresponds to k equals 0. S2, it's 1 plus 1/2. Okay, well, that's 3 halves. S3, 1 plus 1/2 plus 1/4. So we have to add 1/4 to 3 halves. 3 halves is 6/4, so I think that you can check my math, but that's 7/4. Okay, so I'm kind of interested in looking at lots of these partial sums. So I've got a graph I'm going to switch over to in Desmos. Hopefully, if you haven't already done so, you'll check out the video on how to graph sequences in Desmos, because I think it can really enhance your understanding of this material to visualize it. So I'm going to continue the same coloring scheme in Desmos when we get there. So the partial sums, we're going to be looking at partial sums and the terms. The partial sums I'm going to be writing in blue, and they're going to be drawn as dots. So when we look over here, you can stop this video and rewind to this if you need to. But so we're going to be looking at blue dots when we are plotting partial sums, And in addition to the color for the terms of the sequence, I'm going to be plotting those in the color red, but I won't use dots, I'll use X's. Okay, so let's switch over to Desmos. You know the example we're talking about. It's this example 2. We're looking at these sums. We've written out the first 3 partial sums, and I want to look at more, and I'm lazy, and I don't want to do the arithmetic by hand. So let me beg Zoom to let me switch my window. I've got it ready for us. I think you can see this. I tried to kind of even blow it up a little bit. Uh, don't worry too much about these panels over here. It's kind of more for me and to make this picture, but you're looking at the XY plane, and right now you see a blue dot on top of a red X, if your eyes are sharp, and that's because, well, the first partial sum and the first term of the sequence are the same, right? They were both equal to 1, so they're plotted at level 1 there. Now this is my counter. It's capital N in Desmos, but don't worry about that. So I just moved it over. So now what are we looking at? The red X is the sequence term 1/2. Yeah. What's this blue dot? That's the first partial sum. And remember, we just computed it. It was 1 plus 1/2 or 3/2. Okay, cool. Let's look at the next term. Red X is the term we're adding. That's a quarter, because we've gotten out to the count, the exponent on 1/2 being 2. What's this value? Well, that's the 1 plus the half plus the quarter. That's your 7/4, your 1 3/4. All right, so those are the 3 that we computed by hand. And now the cool thing about Desmos is I can just have it compute this as fast as I want. All right. So what is this picture telling us here? Well, a couple of things. It's kind of a busy picture. It looks to me, as we were looking at n getting bigger and bigger, I took it all the way to 20 there now. It looks to me that both of these sequences are converging. I don't have proof of that, but well, you knew that the red sequence from our work in chapter 11, section 1, powers of 1/2, because 1/2 is less than 1, they're going to go to 0. And that's what we're seeing here. Those red X's have certainly descended to 0. In fact, they're getting there in a hurry. I mean, if you think about these numbers, 1 over 2 to the 10th, that's 1 over 1024. It's a very small number. 1 over 2 to the 20th. It's a mind-bogglingly small number. Okay, and it looks to me like the partial sums have approached something too. If I'm just going to take my cue from Desmos, it looks like they approached 2. Okay, so what's going on here? It kind of makes sense that the things we're adding are getting so small. Notice as soon as these red X's kind of almost hit, none of them are on the X-axis, but as soon as they're almost there, the blue dot changes height, doesn't change very much. And that's because, as we move from one of these blue dots, look at 11 to the next one, what did we add to it? We added basically 0. And we added basically 0, and we added basically 0. So those sums aren't going to change very much. All right, let me switch back real quick to the whiteboard because I just want to write down what we just conjectured. It looks to me from the Desmos graph, I have a guess. It looked to me like this series, the sum as n goes from 0 to infinity of 1/2 to the k, it looked like it converged. And in fact, it looked like it converged to 2. Yeah, so that's just the symbolism of what we would write down. I don't have a proof of that. I don't know that those numbers, that those partial sums limited to 2, but that Desmos graph was pretty convincing that that's true. All right, I want to actually switch back to the Desmos graph. Before I do it, actually, maybe this is a better place. I can change in that fancy Desmos thing that I made. I can change this number. Yeah, so it's a half in the screen we were just looking at. When we go back, I'm going to change it. It's called R in the Desmos, and I just kind of want to play around with it a little bit to see what happens. So I'm not trying to do something fancy here. This is kind of the way I like to do mathematics. I like to experiment and play around and sort of just keep asking myself what's going on here. So you can see up here now, this top pane kind of makes more sense. I let this variable r equal a half, okay? That's why we were looking at 1/2. Let me reset everything and bring back n to 0. And let's change this r. Let's make it a little smaller. I've set this up. Right now it's a quarter. So sorry if this is frustrating. I don't want to flip back to the whiteboard, but I'm looking at the sum of 1/4 to the k as k goes from 0 to infinity. All right. And I want to know, or as a 1/4 to the n, as n goes from 0 to infinity. It doesn't matter what we call the exponent. Those two dots are on top of each other at the beginning because, again, the first partial sum is always the first sequence term. And this time we let them go. There we go. Notice again, the terms that we're adding are getting very small. They're almost 0, and it looks like this sum is converging. It's not clear exactly what, some number between 1 and 2. Okay, like that demonstration. Let's change r again. Let's change r again. It was a quarter. We've already done a half. Let's try 3/4. Okay, blue dot and red X are on top of each other. First term and first partial sum are always the same. Let her run. What do you think? Notice that the blue dots took longer to level off. That's because these red X's were a little bit slower at approaching the axis. But again, once the terms, the things I'm adding, once they got kind of small, it looks like this thing leveled off. Cool. Let's try it one more time. A couple more times, really. Let's like RB1. All right. So this time, what are we doing? We're adding the sum as n goes from 0 to infinity of 1 to the n. Well, every power of 1 is 1. So the blue dot and red X are on top of each other because the terms, the first partial sum is equal to the first term. But now, when I do this, I'm actually going to stop a little bit earlier. So the r's aren't changing, right? Because why? 1 to the 0 is 1. 1 to the 1 is 1. 1 squared is 1. 1 cubed is 1. The r's are always the same. What are these blue dots? These are just the partial sums. 1. 1 plus 1 is 2. 1 plus 1 plus 1 is 3 and 4. So it doesn't look to me like this series converges at all. Those blue dots are just shooting off to infinity because look, I'm just adding 1 plus 1 plus 1 plus 1. Of course that doesn't converge. Yeah, good. Situation even gets worse if we make r bigger than 1. If we make r 1 1/4, then the powers, the terms that we're adding, they're not only not going to 0, they're getting bigger. So the partial sums just shoot off to infinity even faster. Yeah. So what are we stumbling around here? I wanted to do this demonstration to try to convince you that when you're taking some series, the behavior of the terms, the red X's, has to be a certain way if the series has a chance to converge. If those red X's themselves are not going to approach the axis, then the things you're adding together are not getting small. The sum is going to become huge, right? If the red X's do approach the axis, then you have a chance for those blue dots to accumulate at something. All right? So you can pause and let that kind of soak in. I'm going back to the whiteboard. No pausing for me, but you can always pause and take a break in these things if it's hard to concentrate or I'm throwing a lot of information at you at the same time. Okay, so here I've taken from your book a theorem. It's called Theorem 6 in your book. You can look at it on page 713 if you want. And this is what we were just discussing. What does Theorem 6 say? Theorem 6 says that if you have an infinite series and it converges, so its sequence of partial sums has some limit, then the limit of the terms themselves, in fact, let me, I want to change to keep this all color coded. If the series is convergent, then the terms themselves have to go to 0, right? I'm just translating that down here. If the partial sums, I wrote it in blue, have a limit, then the things you're summing have to become small. Yeah, If the sum is going to accumulate to something finite, then the things that you're summing would have to become small. Or if I rephrase that using a little bit of logic, the contrapositive, if you've taken your logic course, a rephrasing of that is that if the terms don't get small as n goes to infinity, if those red x's in my Desmos picture are not approaching the x-axis as n goes to infinity, then there's no way that the series can converge. The sum cannot be finite. And that rephrasing is usually referred to as, your book is calling it here, the divergence, the test for divergence. Most books, and me included, call it the divergence test. So the divergence test says exactly that if the terms that you're adding don't get small, so if that limit doesn't exist or they don't approach zero, then there is no way that the sum can converge, right? So this is called the divergence test. Let's use it. Let's use it in an example here. I've got an example cooked up. I want to show that this series, the sum as n goes from 1 to infinity of 2n plus 1 over 5n plus 1, I want to show that that series converges. So my sum is the 2n plus 1 over 5n plus 1. So I want to look to see about the terms. So I take the limit as n goes to infinity. This is why section 11.1 is before 11.2, of not the sum, but just the terms. Okay, and you can pause the video and work this out on your own. It's good practice for you, or maybe you can just glance at it, but I'm just going to write it that limit is 2/5. That limit is 2/5, which is not zero. So this series diverges. Okay, that series diverges. The series diverges by, I'm going to use an acronym, the divergence test. We'll just DT for short. Series converges by the divergence test. Let's check out this one. Last example here in this lecture, example 4, I'm going to ask the question, does the series as n goes from 1 to infinity of cosine n diverge or diverge? Let's check this out graphically. Let's go back to Desmos and graph terms and partial sums. I've got it cooked up to do it. Let me share my Desmos window with you. Here we are. I've got the series. The sequence is cosine of n. I'm looking at its sum. I'm letting k go from 1 to n of cosine of n. So it's going to, in the blue dots are the partial sums. The blue dot is on top of the red x because the first partial sum is always the first term in the series. And let's just see what you think. The red x's are the things we're adding. The blue dots are what they add up to. Is it enough to get you to have a conjecture? So the things that I'm adding, they're red x's. Well, there was a positive one and there was negative, so I was subtracting a little bit. That's why the second blue dot is lower y value than the first one, because we added a negative number, and we added another negative number, and we added another negative number. But then we added a positive number, so this blue dot started coming back up, and then we added a positive number, and so on. So maybe this isn't enough to see. Maybe you want to look at some more. Let's let n get a little bigger. Maybe 3, let's look at 3 times as many. I also need to change my x scale if I want to go out that far. So we said 60. We can do it. Okay. Are those blue dots approaching something as n goes to infinity? It looks to me like no. Those blue dots are all over the place as n goes to infinity. So how can we write something down? Maybe you don't want to reason by a picture. You want to write something down. So I have a guess of what's happening. And then, well, if I take the limit as n goes to infinity of the cosine of n, right, the cosine function just keeps oscillating between -1 and 1 as n goes to infinity. Cosine is a continuous function. So I can just ask myself, well, as n goes to infinity, what happens to n? Well, it goes to infinity. And so the cosine of that is going to keep going between -1 and 1. That limit doesn't exist. So this series, n equal 1 to infinity of the cosine of n, diverges by the divergence test. Okay, I'm going to end with just kind of a word of warning. The divergence test never lets you conclude that a series converges. It can only tell you when it diverges. If you take the limit of the nth terms and you do not get it, you get something that doesn't exist, or you get something that isn't zero, then you can say that series can't converge. But if you take the limit, I'm just going to end our lecture here with the same example that we began. Say this series, if I take the limit as n goes to infinity of 1 over n, I get 0. So be careful. I cannot conclude from that calculation that this series converges. I don't know. This series, the divergence test, has failed. It failed in the sense that I still don't know if this series, I'm going to write a little faster here because we're almost done. I still don't know if this series converges or diverges. I need something else. Maybe that'll motivate you to stick with me through section 11.3. Still don't know. Maybe that series converges, maybe it diverges. You could make a Desmos plot. Check out my little code on the left. You could make your own little sequence of partial sums over there. Make a Desmos plot and see if you can decide, but I don't know. But I'm just trying to caution you that when you take the limit of the terms and you do get 0, then unfortunately the divergence test doesn't have anything to say. Okay, thanks for paying attention, and I will see you in 11.2 part 2.